topic is about simple DC circuit and the resistance. So we know that if we have any conductor, it has a particular length and the cross-section area, okay? And the different conductors, they all have a little bit of resistance, preventing current to rapidly go through, preventing infinite amount of current. So the resistivity is determined by the particular material. For example, gold has a small resistivity, and some other metals like aluminum has a higher resistivity. And also, depending on how long this conductor is, you can imagine a very long traffic line is going to give you a larger resistance. And also, how wide the conductor material is. Basically, if you have a very wide highway, large cross-section area is going to give you smaller resistance. That's what happens for one conductor. However, if we are talking about ideal wire, not very long, just some ideal situation, a couple meters or so, those metal wire or couple wire, they have very, very, very small resistance, and we typically ignore that and consider that to be zero. And only in our devices, when we really have resistors being made very, very thin and a very small cross-section area and very, very long to round up, and then we have some noticeable resistance. And what resistance is going to do for us? Basically, if we apply voltage, applying a battery, and apply a voltage difference, I have positive here, negative here, and this voltage is going to provide current in your circuit. And if we know the voltage difference across one particular resistance, then we can know the current. Basically, in order to measure the resistance, we measure the voltage difference between these 2 points, that's delta V, and we measure the current going through this part, that's I, and the ratio of that is your resistance. Your resistance for a particular resistor typically is a constant. However, if you increase the temperature or do something different, the resistance may change. For most of metals, when you increase the temperature, the resistance increases. For semiconductors, when you increase the temperature, the resistance reduces. And in this class, we only care about assuming that our resistance are constant, and let's solve some of the problems, unless otherwise noticed. So, rearrange this equation a little bit, we figured out that the current through any particular resistor equals to delta V over R, but this is a very dangerous equation if you forgot to identify which delta V and which R. It only works if you are talking about the particular voltage difference across this particular resistor, instead of the total delta V or another delta V across somebody else. So make sure that your subscript notation matches everywhere when you apply this equation. And we know that if we have resistors in series, one after another, that's like adding and adding and adding this journey, make it longer and longer. We're going to add the total resistance together to give you the total effective resistance. So 3 of them adding together is as if we have one resistor, which has a larger resistance equals to R1 plus R2 plus R3. You can add more, okay? However, it is very, very, very important to notice when all these resistors are in series, the amount of current coming in goes through the first one, goes through the second one, goes through the third one. The current everywhere, I1, I2, I3, and I total, they are all the same amount of current. Nothing is being split out to another path. There's only one loop, and the current is equal everywhere. Okay? And how to figure out that current? That's your total current. And keep in mind that your total current in this situation is your total voltage. Delta VT, in this case, is the voltage epsilon provided by the battery, divided by the total resistance, R1 plus R2 plus R3. The reason we care about this equation to figure out the equivalent resistance is that using the total voltage and the equivalent resistance, we are able to figure out the total amount of current. Okay? So, for example, when we have such a circuit, what can we do? We notice that we have R1 in series with a big chunk, and then in series with R4. But here inside this big chunk, we have two resistors. They are not going one after another. They are parallel, like here. What happens if you have different resistors when they are in parallel to each other? And in that case, we see the current going through I1, and the current I2, and the current I3. They are not necessarily equal to each other. It's like some of you go to a movie, some of you go to a physics class, some of you go to a chemistry class. They are independent from each other. They are not at the same, okay? However, they are related that if you add 1, 2, 3 groups of current, adding all of them together equals to I total. The I total is being split into 1, 2, 3 parts, and after that, they all add together back in I total. So that's important. Again, how can we solve this problem? We use this equation to figure out the equivalent resistance. When you have 1, 2, 3 in parallel, it's as if we have one big R equivalent representing all of them. And then using the total voltage divided by that gives you the total current. After you figure out the total current, you do something more to figure out each individual current. Let's do this question as an example. So if we have R2, R1, R4 of them, and then what happens is that R2 and R3, they are in parallel. Together, it's like R parallel, okay? So this circuit can be simplified as R1 and R parallel, which represent this part, and then in series of R4. Okay, using this equation, we know that R parallel is equal to 1 over R2 plus 1 over R3. Not yet, that's 1 over that. We need to reverse that to give me R parallel. Once that is done, the R total equivalent, the total resistance, R total is equal to R equivalent. It's equal to, we have 1, 2, 3 of them in series. So that's R1 plus R parallel plus R4. Okay? And then, why do we care about this equivalent? Because then we can figure out the I total is simply equal to the delta V total, which is the battery voltage epsilon, over R equivalent. Step 1, combining these two. Step 2, adding them. Step 3, when you figure out the total equivalent resistance, you are using the total voltage divided by that gives you I total. Okay? And it is a big no-no if some of you say, oh, I know, I1 equal to the epsilon over R1, I2 equal to epsilon over R2, That's big no-no. Entirely wrong. Why? Because this voltage is divided into 1, 2, 3 steps. You did not apply this, for example, 5 volts battery to R1 all by itself, to R2, R3, R4 all by itself. It's a big no-no to plug in the total voltage to figure out the individual I1, I2, I3. But it's okay to plug in the total voltage and the total equivalent resistor to figure out the total current. Once you figure out the total current, what else? Let's see. We have a current coming out. This is I total. And I total keeps going. I1 is equal to I total because everything turning around goes through R1. And what happens? It's got split into two parts. So I have another equation which says I1 equals to I total, which we already figured out, and also equal to I4. We're going to talk about that later. However, what's important is this. I total equals to I2 plus I3. We have some current going in this direction called I2, some current going in this direction called I3. They are different. Both are smaller than the total. Okay? Can we solve this equation? If we know this, we don't know how they distribute. Also, another important thing is that notice when we have them in parallel, they have a different current. However, those wires are ideal. Everywhere here, 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 here. All these 3 points, they have the same potential because we consider wires have no resistance. And all these 3 points have the same potential. As a result, when they are in parallel, something extremely important is that delta V1 equals to delta V2. The voltage across this guy is equal to the voltage across this guy is equal to the voltage across this guy. So, the current I1 multiply R1 equals to the I2 multiply R2. So in this case, we have I2 multiply R2 that gives you the voltage difference between these 2 points, which is equal to I3 multiply R3 when 2 and 3 are in parallel. Using these two equations, we will be able to solve I2, I3 separately. Notice that if you divide one of the R to the bottom, if you divide this R to the bottom, if you have a large R, you have a small current. If you have a small R at the bottom, you're going to have a larger current. And then you can substitute this back to this equation, solve for each one of them. Okay? And then you know each individual I1 and I2. What happens later? What happens later is that I2 and I3, they add together and give you back the total current going through R4. That's why R4, the current going through that, is equal to the total current. This is how to solve this problem. To remind you, when resistors are in series, they add directly together. When resistors are in parallel, they add reversely. Okay? And also, when resistors are in series, everywhere you have the same current. I1 equal to I3 equal to I4 equal to I total. They all have the same current, but each individual one takes a small portion of the total voltage or total potential difference. And each one, the voltage across the first resistor equal to I1 R1, and I1 equals to the total the current delta V total over R equivalent. As a result, this is an important voltage divider idea. For each individual resistor R1, it's going to occupy a certain percentage of the total voltage. And that percentage is determined by the amount of R1 comparing to the total. So if you are talking about R2 comparing to the total resistance, that percentage multiply the total voltage gives you how much share this second resistor occupies. That's the voltage divider idea. They share the current and they have the same current, but they divide the voltage into 1, 2, 3 different steps. While you have something in parallel, however, they all have the same voltage difference, delta V, delta V, delta V. So the product of I and R is the same. However, they have different value of I. Larger resistance, imagine a very narrow way going home. It's going to have a small traffic flow. A very wide highway with little resistance is going to have a very large flow. Okay, different pathways have different current, but the total adding together to give you the total current. Okay, now let's think about the power. When you have a current going through resistance, and this resistance is going to heat up, which consumes some power, And the power is equal to delta V multiply current. The bigger the voltage difference, the bigger the power, or the bigger the current, the bigger the power. Okay? And for each particular resistor, notice that if we are talking about number I, we are using the current of number I and the resistance of number I. Okay? So now let's compare R1 and R4. Which one consumes more power? How can we do that? We would like to compare the difference between R1 and R4. We try to figure out something in common. R1 and R4, they both have the same total current. If they both have the same total current, we would like to look at this equation, knowing the current part, current square is the same. Then we can easily compare R4 and R1, whichever has a larger resistor is going to consume more power. When things are in series, whoever has a larger resistor consumes more power. How about the power consumed by R2 and R3? Which one is bigger? You may think, oh, who has a larger I? Actually, this time, because they are in parallel, between these 2 points, they have the same voltage difference. If they have the same delta V and they have the same delta V square, we can compare these two. Obviously, power equal to this over that. If you have a small r, you are going to have a larger power. When objects are in parallel, they will provide you the same amount of delta V. If you have a small r, you're going to have a bigger current, you're going to have a bigger power. So, in series, larger r, more power, same current. In parallel, larger r, small current, small power, because they have the same voltage difference. Okay,